In this video, I'm going to show you how we can write the form of a particular solution for a non-homogeneous differential equation. Here, we want to discuss about the case that the right side of the non-homogeneous differential equation is the product of a polynomial by an exponential function. Let me show you an example. For example, consider this differential equation y double prime plus y prime minus 2y equals to 3x minus 4 e to the x. This differential equation is a non-homogeneous differential equation, and the right side of the equation is a polynomial, which here is of degree 1 and is multiplied by an exponential function e to the x. We want to see how we can write the form of the particular solution for this differential equation. Remember that the general solution, if we suppose y to be general solution, is the sum of complementary and the particular solution. The complementary solution is part of the solution that is related to the homogeneous differential equation. So for finding the complementary solution, we have to write the homogeneous corresponding equation to this equation, which is y double prime plus y prime minus 2y equals 0. By solving this equation, we can find the complementary solution. For solving this homogeneous differential equation, we write the characteristic equation, which is r squared plus r minus 2 equals 0. For finding r, you can use quadratic formula, or you can factor this quadratic equation like this: r minus 1 times r plus 2 equals 0. Now if we set each bracket separately equals 0, r equals 1 and r equals negative 2. Because here in our characteristic equation we have two distinct real roots, so the complementary solution is c sub 1 e to the x plus c sub 2 e to the negative 2x. So this is the complementary solution. Now let's find the form of the particular solution. For writing the particular solution, note that we have a polynomial of degree 1 because we have 3x to the 1, which is multiplied by e to the x. Whenever in the right side of our non-homogeneous differential equation we have a polynomial multiplied by an exponential function, the general form of the particular solution is always a general polynomial with the same degree, and because here we have a degree 1 polynomial, so we have to put only ax plus b. But if here we had x2 in this bracket, the form of the polynomial should be a degree 2 polynomial like ax2 plus bx plus c. And then we have to multiply this, of course, with the exponential function. So this is the general form of the particular solution for this differential equation. But always note to this point, you have to compare the terms in the particular solution with the terms in the complementary solution. If any terms here duplicates in the complementary solution, then the form of your particular solution is not correct. And we have to fix it with multiplying the term in the particular solution with the smallest degree of x that prevents this duplication. Note that here, if we multiply e to the x in the bracket, we have ax e to the x plus b e to the x. So we have e to the x and x e to the x. These are the two functions that we have in our particular solution. If you compare these two terms with the terms that we have in our complementary solution, you can see that e to the x is duplicated here. We have the same function here. And so this shows that this is not the correct form for the particular solution. How we can solve this? It's really easy. Just multiply this by x. And this solves everything. Now, if we multiply this e to the x and x in the bracket, easily you can check that you don't have any common term between the particular solution and the complementary solution. First, let's multiply x in the bracket. Then we have ax2 plus bx times e to the x, which now, if we multiply e to the x in the bracket, we have ax squared e to the x plus bx e to the x. And so this expression is the form of the particular solution. And if you want to find a and b, you have to find first and second derivative of this function, plug in here, and then by equating coefficients, you can find a and b. But in this video, our focus is on just writing the form of the particular solution, not finding these unknowns. If you want to learn how we can find a and b, these unknowns, in the method of undetermined coefficients, you can watch my other videos about solving non-homogeneous differential equation. So let's review why we multiply this by x. Whenever the terms in the particular solution are duplicated in the complementary solution, we solve this problem by multiplying the particular solution by the smallest degree of x that prevents this duplication. It means that if even when we multiply x, we have common terms between the particular solution and the complementary solution, multiply the particular solution by x squared or x to the 3, but the smallest degree that prevents the duplication, which usually x solves the problem, as we did here. This was the case 5. I forgot to write this here. Now let's move to the other case for the non-homogeneous differential equation. In this case, we want to talk about the case that we have the product of a polynomial by sine or cosine functions. Let me show you an example. Consider this differential equation: y double prime plus 9y equals to 2x minus 1 cosine 3x. The general solution is y complementary plus y particular. For finding y complementary, the complementary solution, we have to write first the homogeneous differential equation corresponding to this equation, which is y double prime plus 9y equals 0. The characteristic equation is r squared plus 9 equals 0. For solving this equation, you can use the quadratic formula, or you can move 9 to the other side. We have r squared equals negative 9, And if we take s square root r is plus minus s square root of negative 9. But note that s square root of negative 9 is s square root of 9 times s square root of negative 1. Square root of 9 is 3 and the square root of negative 1 is I. So we can write this as plus minus 3I. And also note that here is 0. We can suppose 0 to be here. Remember that when we have complex roots like this, in general a plus minus bi, for writing the complementary solution we use this formula: e to the ax, a is this number which in this case is 0, times by c sub 1 cosine bx plus c sub 2 sine of bx. And here b is 3. Based on this formula, the complementary solution is e to the 0x, because here a is 0. But e to the 0 is 1, so it's not necessary to write it. So just we write this: c sub 1 cosine 3x plus c sub 2 sine 3x. This is the form, this is the this is the complementary solution. Now we want to write the form of the particular solution. In the right side of this equation, we have a polynomial which is multiplied by a trig function. This polynomial is of degree 1, and when we have a polynomial of any degree multiplied by a trig function, the form of the particular solution in general is a polynomial with the same degree. If this is degree 2, degree 3, put the same degree here. Here the polynomial is of degree 1, so just we have to put ax plus b here. But if this was degree 2 or higher degrees, we have to put the same degree here. Times by cosine of 3x, and also put a polynomial with the same degree, not the same coefficient, but with the same degree. So instead of ax plus b, cx plus d times by sine of 3x. Note that maybe you think, why we have to put sine of 3x here? We have only cosine here. But note that when we take derivative of cosine and sine, they switch to each other. That's the reason that it doesn't matter we have only cosine here or sine or both. Always when you write the form of the particular solution, you have to put both of them here. So for each of them, we have to multiply by a polynomial, and we have to put both of them here. It doesn't matter if we have only cosine or sine. Now, as usual, let's compare the terms that here we have with the terms in the complementary solution. We know that the duplication should not happen. If we multiply cosine of 3x in the bracket, we have ax cosine of 3x plus b cosine 3x. And if you multiply sine, we have cx sine of 3x plus d sine of 3x. X cosine of 3x is not repeated here, but b cosine 3x cosine 3x is repeated here. Also, sine 3x is repeated here. So, the terms in the particular solution are duplicated here. And to solve this problem, we have to multiply this by the smallest degree of x, smallest positive degree of x, that prevents this duplication. And in this case, x to the 1 solves the problem. Because if we multiply x in this bracket, then we have ax to, let me show you what happens. So this is the form of the particular solution, but I want to show you why this works completely well. If we multiply x in the bracket, we have ax2 plus bx cosine 3x, and don't forget to multiply x in the other term, cx2 plus dx sine 3x. Now if we multiply cosine in the bracket, none of the terms is duplicated. Also, if we multiply sine in the bracket, none of the terms is duplicated here. And so, this is the form of the particular solution for this differential equation. Or if you like, you can write it in this form. It's the same function. Now let's go to the last case. Now consider the case that we have the product of a polynomial by an exponential function which is multiplied by sine or cosine function. Let me show you an example of this case. Consider this differential equation. Y double prime minus 2y prime plus 2y equals to 2x minus 1 e to the x sine of x. A polynomial multiplied by an exponential function which is multiplied by a trig function, the product of three different types of functions. As usual, the general solution is the sum of complementary and particular solution. For finding the complementary solution, first we write the homogeneous differential equation. We set left side y double prime minus 2y prime plus 2y equals 0. The characteristic equation is r squared minus 2r plus 2 equals 0. And for finding r, we can use quadratic equation, quadratic formula. We cannot factor this, so we use the quadratic formula for finding r. R equals negative b. Remember the quadratic formula: negative b plus minus b square root of b squared minus 4ac over 2a. So r equals 2 plus minus negative b is negative, negative 2 is 2 plus minus b squared is 4 minus 4 times 1 times 2 is negative 8 over 2. If we simplify this, r equals 2 plus minus, note that 4 minus 8 is negative 4 and negative square root of negative 4 is the square root of 4 times the square root of negative 1. And this equals 2i because the square root of 4 is 2 and the square root of negative 1 is I. So we have 2 plus minus 2i over 2, which if we divide the terms in numerator by denominator, r equals 2 over 2 is 1 plus minus 2i over 2 is also 1i. Note that a is 1 and b, the coefficient of I, is 1. So the complementary solution is e to the 1x, because a is 1, e to the 1x or e to the x times y, c sub 1 cosine 1x again, plus c sub 2 sine 1x or x. This is the complementary solution for this homogeneous differential equation. If you don't know how to write the complementary solutions or how to solve homogeneous differential equations, you can watch my video about solving homogeneous differential equations of second order or higher order. Now we are ready to write the form of the particular solution. Here we have a polynomial of degree 1. The form of the particular solution for this part is ax plus b as usual. Because we have a polynomial of degree 1, we use this polynomial for this part. And because this polynomial is multiplied by e to the x sine of x, we have to multiply this also by e to the x sine of x. But note that whenever we have sine, in the writing the form of the particular solution, we have to put the same form with cosine. It doesn't matter we have sine or cosine, similar to the previous question. Whenever you have sine or cosine, when you write the form of the particular solution, you have to include both of sine and cosine. And because here we use a and b as unknowns, here we use c and d. These are the undetermined. These are the unknowns of the method of undetermined coefficients, which we can find them by substituting this in y and finding the derivative of this and substituting for y prime and y double prime. But in this video we are not looking to find these unknowns. As usual, let's compare the terms in the y particular with the term in y, the complementary solution. Note that here we have b e to the x sine of x and d e to the x cosine x. And exactly here we have e to the x cosine of x and e to the x sine x. So this shows that the terms in particular solution are duplicated in the complementary solution. And because we don't want this happens, we have to multiply this by the smallest degree of x to solve this problem. And x solves this problem. If we multiply this by x, now the terms here are not duplicated here. None of the terms here appears in the complementary solution. If you like, you can write the particular solution in this form: ax squared plus bx e to the x sine x plus cx2 plus dx e to the x cosine x. And this is the form of the particular solution for this differential equation. I hope by watching these videos you have learned how to write the form of the particular solution for non-homogeneous differential equations. If you liked these videos, please subscribe in my channel. Thank you for watching.